Hello everyone, we are Team Foxglove and our project is Bitcoin Alpha Trust Network Analysis. I am Harsh, my teammates are Kavya, Arjun and Karam. The dataset that we're using in this paper is Bitcoin Alpha. It is a trust network graph comprising of user ratings in Bitcoin platform. It is a signed edge weighted network where members rate other members from a scale of -10 to +10 in steps of 1, 10 indicating total trust and -10 indicating total mistrust. Each row in the dataset consists of source, target, rating, and timestamp at the time of rating, measured in seconds. There are 3,783 nodes and 24,186 edges. Part one of the project is computing centralities and the relationship between them, where we are calculating the various centralities and then doing the correlation analysis and then ranking them accordingly. And finally, we observe the common trends among them and use a polynomial regression model. So as seen in this correlation graph, there is a high linear correlation among in degree, out degree, degree and betweenness centrality, which can be seen from the color-coded scale on the right. -1 and +1 indicating high correlation. So as can be seen, closeness centrality has the least correlation with other measures, and overall degree centrality, being a symmetric measure, exhibits the same behavior in comparison with its asymmetric counterparts, which are in degree and out degree. So this conveys the redundancy of direction in these measures. So from further on, we'll only be using degree centrality for our data analysis. Okay, so next is trends in centrality analysis, where we observe three trends from the data set. First is the rank of eigenvector and closeness centrality is lower than betweenness and degree centrality. Uh, this could mean that the node is enclosed in a cluster away from the rest of the network, and it connects a small group of nodes to many others. In the Bitcoin dataset, nodes with these properties are acting as brokers in the network, connecting a dense, isolated cluster of nodes directly to the peripheral nodes. The second trend is lower rank of betweenness centrality as compared to other centrality measures. This implies that there could be multiple paths in the network to reach various nodes. The third trend we observed is that the closeness centrality has a very low rank as compared to other centrality measures. This implies that nodes with these properties connect a small group of nodes to highly influential nodes. Next, we developed a polynomial regression model using sklearn Python model toolkit. We could ascertain the relationship of closeness centrality, and this model uses degree 2, in which 70% of the data was used for training and remaining 30% for testing. So we came up with a quadratic polynomial wherein there are three variables x, y, and z. X for degree centrality, y for eigenvector centrality, z for betweenness centrality. And the function f of x, y, z gives the closeness centrality. And these were the various coefficients that we could obtain. So from this, the RMS error for training data, the root mean square error was 0.0275. The root mean square error for testing was 0.0272. And the mean value of the actual data, which is the ground truth, was 0.2363, and for testing data was 0.235. Now to give the goodness value of the training data, we used a parameter called sparsity index, which is the RMS error of predicted values upon the mean of true values. So the calculated value of that was 10%. This implied that the model is actualized and that it is closer to the actual value.
Next, we move on to node partitioning based on centralities. Grouping of nodes based on centralities will give a better understanding on levels of importance upheld by various nodes in the network. This also helps in categorization of type of influential role played by each node. To accomplish this, we have invested in two techniques, namely feature selection and dimensionality reduction. In this case, the original feature space is converted into a reduced or a new feature space with fewer dimensions. This reduction is achieved either by selecting a subset of original features, that is feature selection, or by mapping them into an entirely different feature space, that is dimensionality reduction. So these techniques also help in better interpretability of results. So for feature selection, we have employed two techniques, namely random forest regression and feature agglomeration. In random forest regression, a random forest algorithm is employed which helps to weigh the importance of each feature in the model. It does so by calculating the impurity a tree node using that feature induces across all trees in the forest. Hence, a random forest regressor was used using the sklearn package of Python. So from this graph, it is quite clear that betweenness had the lowest importance. This model was made based on eigenvector as the output and regression parameters found using closeness, degree, and betweenness. So our next technique is feature agglomeration. In feature agglomeration, agglomerative clustering performs clustering by considering each sample as a cluster of its own and then recursively merging the samples into clusters. It uses a bottom-top approach of clustering. Feature agglomeration uses this technique to merge similar features together. This was implemented on our data, and it was found that degree and betweenness were merged into their arithmetic mean as a single feature. And hence, based on the above two observation, it was declared that betweenness centrality could be eliminated from the feature space. Also, there was a strong correlation between betweenness and degree centrality, which helps in further deciding that betweenness could be eliminated. So the remaining three features were visualized as a scatter plot in 3D using MATLAB. So x-axis was taken as a degree, y-axis was taken as eigenvector, and z-axis was taken as the closeness. So from this data, it is quite clear that we do not have evenly shaped clusters. There are uneven sized clusters, and they are also non-ellipsoidal with irregular shapes and flat geometry. So for such a fit, a Gaussian distribution model can be employed. So it was decided that we would be using GMM to fit our data. And our next challenge was estimating the number of clusters for the Gaussian mixture model. For this, we have employed two techniques, namely Bayesian interference criterion and the silhouette score. So Bayesian interference criterion is a measure that gives us quantifying score of how well the model fits the unknown distribution. Lower the scores of BIC, the better the model is fitting. Following this criterion, it is observed from this figure that the more number of clusters, the better is the fit. Hence, it can be reduced that BIC does not penalize complex models from overfit in this case. Since the curve is monotonic with different slopes in different regions, gradient of BIC can be used to understand the point of biggest slope change. Therefore, we performed this, and after this it can be clearly seen that 5 clusters, the slope is almost constant, indicating that there's no much gain in increasing the number of clusters. Okay, the next technique we employed was the silhouette score. The silhouette score measures how compactly packed and well separated each cluster is. So this is achieved by considering the mean distance between the points in the same cluster and the mean difference between points in the next nearest cluster. The results obtained with this technique further suggest that the usage of phi is an optimal number of clusters. Next, we studied the effects of cost function on various number of clusters. It can be clearly seen from this figure that as the number of clusters increase, the cost function decreases. This is quite evident from the fact that as number of clusters increase, the constraint of generalizing behavior of various samples into clusters reduces. Each sample preserves its own properties when number of clusters is increased to the number of data samples. Hence, the choice of number of clusters is always a trade-off between reducing the cost function and grouping of similar data together. Using phi as optimal number of clusters, the grouping was done, and following inferences can be deduced from the clusters formed. In cluster 1, all the nodes have low values of centralities, indicating that these nodes are not regular users of bitcoins, making very few transactions. They are also not preferred for trading among others. In cluster 2, nodes have low ranks of degree, high ranks of eigen centrality around 1000 to 1500, and high ranks of closeness centrality above 700 to 1000. So our data was actually normalized and then ranked based on rank number 1 being the highest value. So with this case, it suggests that mostly these nodes are enclosed in a cluster far away from the network with direct connection to nodes which do not have connection to influential neighbors. In cluster 3, The nodes followed the similar behavior but more strongly, as their ranks was nearly 2000 to 3000 among all the centralities except degree centrality. In cluster 4, these nodes had lower closeness values compared to their degree and eigenvector centrality. Nodes with these properties are embedded in clusters away from the network but remain connected to many influential and other users in the network. In cluster 5, all the nodes have low ranks of centrality, that is higher centrality values, indicating that mostly these nodes are top influential nodes in the network. There's not much variation in the ranks among their centrality measures.
Final part of our project is analysis of trust in Bitcoin Alpha platform. In Bitcoin Alpha platform, users rate traders based on genuineness of transaction on a scale of -10 to +10. It is hypothesized that when a user is encountered with a fraudulent transaction, he or she takes a quite long time to come back to the network and make their next transaction. This can be considered as loss of trust. In some cases, the user may not even return. One of the major obstacles in this study was the absence of labels for the fraudulent users, which was overcome by using a Burness algorithm to filter out the fraudulent users from the data set. Burness algorithm works in the principle of Bayesian model to understand the type of user rating behavior and the forming a likelihood estimate which measures how much a user deviates from other users or other genuine transactions. After pre-processing using the Burness algorithm, the data was inspected to test this hypothesis. It was found that Bitcoin users, after undergoing a fraudulent transaction, do not lose trust in it and may even return within an average of 8 days. Though the average of the user return was 8 days, the rate of return after a fraudulent transaction varied among users. This was the motivation for us to create a predictive model to determine their next transaction date. First, we analyze the data preparation as removing fraudulent users and prepare a feature space containing rating before fraudulent transaction, the fraudulent transaction rating, their corresponding time instant, and their out degree centralities for training the model. After selecting the feature space, we analyzed which model to be used and we found that LSTM model is best for our scenario. LSTM is an artificial recurrent neural network, and this was used in the fields of deep learning. LSTM also has feedback connections which improve their processing. The model was successfully trained with 70% of training data and 30% of testing data. The model comprised of 3 hidden layers of 50 units each, and the model gave us an RMS error of 0.04 for training and 0.05 for testing. The mean of training and test scores were 0.45 and 0.45 respectively. Now this led to us to believe that sparsity index of less than 10%, which indicated that the model achieved a good fit for the data. Next, we can see a video of the execution of this. On the left is our program. Running the algorithm and training the network. We skip to the 100th epoch. As you can see, the RMS value for training is 0.04 and RMS value for testing is 0.05. Next, we can see that the bar graph plot is used to show the predicted values and actual values to analyze whether our model have predicted accurately or not. Considering this area, we can see that most of the predictions were approximately correct. Finally, we have a line plot also to analyze the prediction and the actual values. You can see that the model emulates the user behavior well. This can be concluded that our model have achieved good results, but to improve these results, we can use more training data.
So from this project, we are able to conclude that polynomial regression model can be used to model data following a nonlinear relationship. Clustering method should be decided based on data distribution and type of clusters that can be derived from the given data. BIC scores are good estimators of number of clusters in GMM. LSTM model is a good estimator to model parameters for a time series data. Evaluating RMS scores and tuning model parameters according to prevent underfit or overfit help obtain better results. Thank you.